Okay, so let us implement our recurrent neural network, and we are going to do it in this setup to analyze this data set of IMDb movie reviews. So it's a data set for sentiment classification. We are going to download this from Kaggle, and here I have the download page here. As you can see, each review has a label, positive and negative. So these reviews are collected to be a bit extreme, to basically make it easier for our natural language processor to classify. So we are going to use this data set, and we built first a vanilla recurrent neural network that takes in each review and predicts the label, either positive or negative. The problem fall into this class. We take in the sequence, and at the end, given the final hidden state, we will classify the review as positive or negative. Things to consider is we are batching variable length sentences, so we have to pad them to all have the same size for the GPU. And also, of course, we need to translate the natural language to numerical values, because that's how computer understand. So to do that, we are mapping each token to an ID. And since we want the vocabulary size to be finite, we choose a max vocabulary size, which is less than the number of tokens. And that means that there are some rare tokens that doesn't get any ID. And we are going to just assign unknown to them. And that will not affect the analysis a lot, because they are not occurring a lot. So we discussed the basics of the recurrent neural network cell that takes in the input and out and the previous hidden, with the tangent hyperbolic activation. We will discuss this while we are coding the cell. So another note on why we need padding. We want to make this special token for the padded values and make sure that our recurrent neural network knows that this is a padded value. And while going forward, if, for example, this last one is just a padded value, we want to make sure the hidden state will be unaffected by this. So making sure that the RNN knows this is a padded value and not updating the hidden state. There are some utility functions here that I included for you. And here basically how to download the data set. And there is a possibility for having a toy data set that in case you want to do prototyping. But I suggest working on the real data set if you have GPU from the get-go. So it's possible to use torch text for downloading the data set, but sometimes because torch text is not maintained anymore, at least updated, so you can just manually download it, and I provided the text here and the code. So like I said, we have to handle the padded values and making sure that they get the special tokens while we are handling them during the RNN architecture. So like I said, I'm going to skip these details and you can look at them. There are some helper functions later when we do the training for plotting the histories and finalizing the presentation of the results. Like, for example, using a confusion matrix, because this is a binary classification. Here I took the opportunity to introduce these decorators that can simplify our code. One of them is this data class that you will see how it can save some of our time and make our code cleaner. So I added an explanation here and how what does this decorator do. I'm planning to compile some of these most useful decorators in PyTorch and include that in the lecture as a Google Colab notebook. Okay, so we are all set to start writing our recurrent neural network. So as we discussed, basically a recurrent neural network cell takes in the token. Of course, the ID of the token, we already did the embedding, and then we have to write a linear mapping here to map the token ID to the hidden space. That linear mapping is basically a weight matrix, and we discussed that we have to take in the previous age again with a weight matrix. In the lecture, I said that we can combine them for the analysis, and actually it helps if we do it in the GPU because we don't need to handle two different weight matrix. So here I'm calling this one weight WHH and this one WIH. Like I said in the lecture, I said we can combine them and we have one larger W, and these two inputs can be concatenated and inputted to that. Due to the issues that we have in vanilla RNN and the fact that when we compute this backpropagation through time, we said that this weight WHH takes an important role because of the exponentiation that they have. So to make our simple RNN works, going to separate them to have WIH here and WHH, and mainly because of the importance of the weight initialization here. Later, when we go to LSTM, we combine them. So you will see that that's not a big deal there. So for now, going to separate WIH and WHH, and like I said, mainly because of the initialization of the weight, and I want to make sure this WHH products will remain stable, and initialization helps here. Okay, so with that caveat, we start the code. We are writing a vanilla RNN cell for now, and then we need to have a linear layer for WIH and WHH. Okay, so just to familiarize you with the lingo here, so these linear layers, we call them sometimes dense layer and sometimes an affine layer. Basically, it's affine because it's a linear plus a bias, right? So when I say this is an input hidden affine, it means that it's a linear layer. Okay, so one thing else, actually, it's good to say here. I don't want WIHH to have bias. This is a classic RNN parameterization. You will see that this will be helpful when we are dealing with the initialization too. Like I said, again, it's about stability of this exponentiation of WHH during the backpropagation. So let's state that the bias is false, and then introduce the initialization here. We are going to have a tangent hyperbolic, so let's use Javier uniform for the WIH. Then for the WHH, which like I said, it's more sensitive. So we want to use orthogonal, that basically we want to preserve the norm across these time steps. So if you remember, as explained in the book also, the largest eigenvalue or the spectral radius of this matrix takes an important role in this exponentiation. So we want to make sure it is scaled. So even taking an extra step to make sure this scaling is happening is advised here. I'm not going to do it here, but scaling with the spectral radius is also handy. And LSTM is not as sensitive as this vanilla RNN. So most of these steps will be unnecessary, really. We have to initialize the bias term for the WIH. So let's do it. Okay. And I think we're good. We can move on to the forward. And remember that we are just writing the cell here. So a torch, tangent hyperbolic of the two, and that's it. So this is our vanilla RNN cell. And then we unroll the sequence of these cells. So let's write this. For the unrolling of these cells, we write this class. So basically what it does is to takes the X, of course, a batch of them, along with the length of them, like we discussed in the processing of the data. So we need to know the length of them. And the main reason is we want to mask those padded values, and we don't want our RNN to process them, right? So that's why we need the length of each sequence, and we get a batch of these padded sequences. And at the end, we want to return the last hidden state to the classification head that we will write in a different class. Okay, so with that, this is the cell, and we can have different type of cell, right? So here we have the vanilla RNN cell, but we can also have the LSTM cell. The cell is defined. We already have a forward method within the cell, so we can use that. And then the rest is basically to make sure we process this hidden state and update them along the sequence and making sure we are not doing it over the padded values. Okay, so that happens all in the forward method. So the input will be, let's say, X, and what is X is basically X is a tensor of this shape. Let me just, so X shape will be badge, length of the time, and the embedding, the embedded tokens. Okay, so that's our shape. Yeah, so if we want this to work with different type of cell that may have different hidden size, right? In that case, we need to take that properties from the cell itself. So in that case, we have basically features of the cell, and using, we will use that to get the hidden size. So for now, to simplify the process, we are going to do this by hand, but I will make sure in the full code that I will share with you, I will include that feature. So because now the hidden size is, like I said, it's determined, so let's just make sure we have it here too. Okay, so now the forward takes in X, the length, and we can think of, so because we only need the last age, we don't need to return the rest of them. So let's just take in X and length. Oh, because I want the most simple code here, let's just write this. So if we write it this way, it basically makes sure that the device is also the same as X. So that's why it's handier. So for t in the range of t, we get the updated age from the cell. So let's call it age candidate that is given by the cell, and the cell starts from X and H. So X and H, and the first H we define it here. So starting with the first H here, which is zeros. Okay, so that's the age candidate. We want to make sure that the mask is constructed. So I'm going to call mask T. We get age. We want age to handle mask. Okay, so basically what we are doing is we keep this age candidate whenever it's not masked, right? So this is just like a 0, 1 kind of mask vector. If it's masked, it will be 0, and it will keep the previous age. So when it's padded, it doesn't update, and it keeps the previous age. I'm thinking even we don't need this. So we're just returning age, right? So this is how we handle this padding, and we make sure h is not corrupted by the padded value, and we return h at the end. So now we can write the end-to-end class that use the cell and the sequence at the classification head at the end, and also embedding at the beginning. Okay. So with that, let's write. Let's call it from scratch RNN. So here we need to know the vocabulary size, the embedding dimension, and the hidden size. The vocabulary size, or the number of tokens that we ID'd. And then here, this is an important component, basically determines the dimension of the embedding of these each one of these tokens. So we embed each one of these tokens. So think of it like a linear layer. So if I write it this way, the self.embedding, it's not within super, so self.embedding is a linear layer that takes in this token IDs and maps it to a e-dimensional vector. Okay. One thing that is important here is we really don't want to learn anything for the padding tokens. So we want to ensure that even the embedding layer doesn't do anything for those pad values. So remember that first we made sure that the pads are not corrupting our age. And here we want to also make sure that it's not corrupting our embedding, right? So we want to force this embedding of the pads to be, for example, 0 vector in this embedding space. So to do that, we have to do some more treatment. So we want to start from some initial, let's say, embedding vectors, Initially, it can be some noise. For example, let's initialize this embedding weight, right? Let's just do with normal, and then with some mean zero and very small standard deviation, right? Then I want to say if self dot embedding is for the padding index, which we determined. So if self dot embedded padding index is not none, so we have a padding index, we want to make sure that its weight is zero. Of this self is just zero, absolute zero. That's that. So we made sure we first mildly randomized the embedding, right? And then we force the rows corresponding to these pads to be exactly zero. I think we have the components, the embedding, let's just call it sequence. And we have the fully connected head, which is a linear. And now we can write the forward method, okay? Okay, so this gives us the logits, right? So if you want to visualize the embedding vectors, you can maybe rename this to something else and directly return this for visualization purposes. Okay, so that's that. We have the RNN. Let's put everything together here. This is our RNN code, and that's basically ready for training. Okay, so because it's expensive to train, let me write the LSTM cell before the training and seeing the result, and then we can compare the two. Okay, so let's carry on with coding our RNN from scratch. We did the vanilla RNN. Now we want to do the LSTM cell first and then doing the sequence, just very similar to what we did with the RNN. We learned that in LSTM, we have a separate memory that is the long memory, and we keep this short-term memory that we call H. So here, unlike in the RNN case, we concatenate this four linear layers into one. I mean, we instead of having one affine for each one of this activation, we put one large linear layer here that takes in xt and ht concatenated, right? Remember that x is the embedding. And we apply one large linear transformation, and that basically maps the input to a 4 times hidden size, because we split each one of them. We basically learn each one of them separately for their respective gates or activation. Okay, so this is basically this. So this is a very nice blog post by Kola that you can look at, and I used the images here. But just to recap, we had the first gate and then the second gate that acts on this candidate long memory, and then the third one. So FT, IT, and OT. So with that nomenclature, let's go back here. We have FT, IT, and OT. So CT at the end will be the FT here that gates the previous C, the IT here that gates the candidate GT here. Okay, so this is GT, and that gives the new correction on the long memory. Okay, so I'm talking about this. And then at the end, we have this gate that takes in the long memory, the updated long memory, and gates it for the new short memory. Okay, so that's what we are going to do. With that, let's write the class. Okay, LSTM cell, and then module, okay, class, LSTM cell, and module. Great, so that's self hidden under S. Let's, okay, like I said, we need one fused affine for all of these gates. Same discussion as before. It's much faster on GPU, and the initialization is not sensitive now. And we are going to use Javier here. And so that's why we fuse all of them together. So let's write one W for all that takes in the concatenated input and return 4 times hidden size. So input size plus hidden size. Oh, I see that the suggestion, note that suggestion separates them. We are not going to do it. Let's just simplify. So we have one W for all. Bias is not false. Let's keep that. So let's do the initialization. So with no Torsionograd. Okay, so recall the gate order is this. So okay, so when we initialize the biases to be 0, it means that initially the forgetting gate will be the so here initially, because like I said, the initial is 0, weights are 0, so we will get taking just the bias here, and sigma of this 0 is 0.5, and so initially we have 0.5 forgetting, which over k steps it will be very fast forgetting. So we are looking at 0.5 raised to k. So the cell forgets very quickly before learns anything. We really want to slow down the forgetting at the beginning. So at the beginning, I like the bias for the forgetting to be rather large. So for example, if the value of the bias here is 1, sigma of 1 will be 0.73, I think. And that means that the forgetting is less, or in other words, the cell leaks less. So information isn't erased immediately. We want to make sure that's happening. Otherwise, it doesn't really learn much. Okay, so for that, I'm going to first get the view of this biases. So I'm going to reshape that to 4 and H. We have 4 of them. So now we address the bias for each gate row. And we are going to make sure the first forgetting is not 0. Okay, so that's good. I think we are good to go. With that, we can write the forward. Okay, so we take in X at step T. Let's just specify that. We take H of previous, right? And we take C of previous. More clear. So X, what's X is the dimension is batch and embedding. H dimension is batch and H. C dimension is B and H, okay? So at the end, what we want from this cell, we want it to give us the new hidden and the new cell state. We just call it cell. Let's also return the value of the gates for visualization, right? We want to know, for example, for a sequence, how these gates are opening and closing. Okay, so now let's do the gate chunking. So we have Z, we have H, that is the hidden size. So this way we have the value of Z corresponding to these chunks, and then we can do the activation. Going to trust this suggestion, and with that, let's, okay, so with that, fix some indentation error that I had, and have this gate setup. We are making the gradient highway here with our additive path that keeps the previous C with the gate, and then write this new G. Okay, so let's expose the short-term memory with the output gate. That's that. Actually, let's just want to make sure we are explicit enough. Okay, so now that's that, and like I said, we want to do some plotting of this gate values. Let's do that. Okay, so that's our cell. Now we can write the sequence of this that unrolls these cells for the batch sequences, right? So LSTM sequence. Let's just make it similar to what we wrote before. Okay, so we will do the same here. So that's our cell. We want a bunch of them. So let's write the forward. Don't know why the indentation is just not doing it. Okay, let's just make this simpler. Going to call this H. Okay, so, and then let's write an empty list for this H and C's. And then for T in range, we have this mask of T. Good, and then we have XT. Let's just, okay, so now we can apply the mask to both hidden and the cell states. Okay, so H will be mask and see that. Great. And then we append all of them, and then let's just return H separately. It will be easier. I mean, last time we didn't really return all of the H's and C's, right? So we can avoid returning them, right? With that, let's write the class from scratch, LSTM, very similar, right? Self-embedding is the same. The sequence now is taking the LSTM sequence, and the FC is that. We do the embedding in it just like before, right? And then write the def for. Okay, so we have everything ready for training. So I'm going to write a train config that is basically shows the training configuration for both RNN and LSTM. So I'm going to write a data class for that and the train config. So let's just write something we can update later. So the good thing about this data class is we can later update it. Let's say 3 learning rate. It's a float, 2e minus, I don't know, 3, for example. Batch size can be how many sequences we load each time. And let's say 128. Let's also define a clipping value for our gradient, right? Let's say 5. I mean, this is essential for RNN, even for LSTM. It helps stabilizing the gates. We can write the training. So I'm going to skip this and just show you the code. Okay, so this is the training. We are using Adam. Adam is very good for LSTM. The cross entropy here is basically a softmax cross entropy for the two classes. Takes in the logits. Here we are tracking the total gradient, and then we do the clipping. And after that, we do the gradient step. Here we have the evaluation, of course, no grad, and then we log. We still need some utility functions for our confusion matrix. And after that, I like to have a function that basically looks at the gates of the LSTM, and we want that for visualization. So I'm going to write that offline. Okay, so here is what we have. So let's go with this embedding dimension and the hidden state, size, the learning rate we already defined. This is how we are loading the data, and then we build the vocabulary, data loaders, and some printing. So let's run them first. So while it's running, let's go to the training of the models. We have the RNN and LSTM, both from scratch. I'm out of CUDA here, so it may take some time. The training script is very similar to what you already know. And at the end, I want to take a look at this LSTM gates for a very obvious case of like, what is this review? Okay. Okay, we have an error embedded. Let's find this. Okay, embedding. Okay, another typo. Let's go back. Oh, I see. This is a self. Okay. Okay, so here we didn't define this. Let's just define it. What else? Oh, yeah, of course. This is, yep, let's fix this. Next error. Okay, some indentation probably here. Okay, so after fixing a few indentation errors, it is running now. So if there is a error, I will let you know. Otherwise, this will take some time because of the I'm out of GPU, so it will take some time. Okay, so here is the result. We see that the loss is going down in training, and you see the accuracy, which is pretty high compared to the simplicity of the architectures and the number of samples. We are getting a good accuracy. You see the gradient norm for the LSTM is keeping very low, and for the RNN, it goes beyond 5, the value that we do clipping. So there will be a lot of clipping in the RNN. Here is the confusion matrix. You see that in the RNN case, we have I would say, good accuracy for both negative and positive. We have better performance for the LSTM. We see that we capture the positives reviews better, so there will be less false positive and false negative in the LSTM case. And here are the gates for this specific example. Amazing, wonderful, perfect movie. Of course, everything is positive here. So the gate, the forgetting gate is not really uh, doing a lot of forgetting. Apparently, it's keeping the memory, the long-term memory over the sequence. Okay, so with that, we will look at more complex RNN tasks, not just many to one. If you remember, we said in the case of classification here, we are giving the sequence or the review and classify it. In the case of translation, for example, translation from English to French, which will be in the homework, we have this sequence and we are translating it to another sequence. So in the decoding part, we have another RNN or LSTM. This will be in the homework, and this architecture is known as sequence to sequence, and it has been the driving force behind Google Translate for many years. And you will see and implement this in the homework.